Solve the equation 2 sine theta plus 1 equals 0 over the interval from 0 degrees to 360 degrees. We'll begin by solving this algebraically. So we have 2 sine theta plus 1 equals 0. We subtract 1 from each side. 2 sine theta equals -1. And now divide both sides by 2. Sine theta equals -1/2. So we want in the interval from 0 degrees to 360 degrees. And since sine is negative, or the value of sine theta is negative, that tells us theta must be in quadrants 3 and or 4. So let's quickly look at quadrants 3 and 4. What we would have in terms of the unit circle are points here where the sine is -1/2, which of course is the y value, would be the negative square root of 3 divided by 2, comma, -1/2. And that line would then give us an angle inside here, 30 degrees. And so from the 180 degrees plus the 30 degrees, that would be 210 degrees. Similarly, we'd have the point over here, which is also a 30-degree angle, and that point would be positive square root of 3 divided by 2, comma, -1/2. And in this case, since this is 360 degrees, we subtract 30 degrees, which gives us the value 330 degrees for this angle that goes all the way around to here. And so the solution set would be written as 210 degrees, comma, 330 degrees. Now let's look at using the calculator to find those exact two values. And so we'll begin by entering the equation in the equation editor. And you can now see that I've entered in there 2 sine of x plus 1. Next, I want to show you that I've changed it to degree mode. So you can see if I move down and over, degree mode is now flashing. The window should be set up like this, where for the x values 0 to 360 with a scale of 30. And for the y values from -4 to 4 with a scale of 1. Pressing graph on the calculator, it then graphs that equation, 2 sine of x plus 1. And now I use the second calc, and I'm finding the intercepts, which is the same as the 0, so I press 2. And now it's asking me for a left bound, so let me make it move a little bit closer, and that's good there. For the right bound, I'm going to move it over past and then press enter. For the guess, I'll just move it a little bit closer and press enter. But then you'll see that it tells us the 0 occurs at x equals 210. By pressing the second calc again in number 2, I'll now find the other intercept, or the other 0. So the left bound will be right, that we'll select for that, move it beyond, and select that as the right bound, move it a little bit closer, press enter, and you can see that it gives us the other 0, which is 330 degrees. Let's look at another part of this example. Solve the equation 2 sine theta plus 1 equals 0 for all solutions. Well, remember, we already found the solution set in the interval from 0 to 360. That solution set was 210 degrees, 330 degrees. To find all the solutions, we now need to add multiples of 360 degrees to each of these individual solutions. So the solution set we would write as 210 degrees plus 360 degrees times n, comma, 330 degrees plus 360 degrees times n, comma, where n is any integer. Similarly, we would have to do the same thing even using the calculator. It doesn't help us in terms of rewriting those individual solutions, but using the calculator we found the solutions 210 degrees, 330 degrees in the interval from 0 to 360, and so the solution for all possible would be exactly what we just found for the algebraic solution. So let's take one more look at that. 210 degrees plus 360 degrees n, 330 degrees plus 360 degrees n, where n is any integer.
Let's solve a trig equation. We want to solve sine theta times tangent theta equals sine theta over the interval 0 degrees to 360 degrees. Our first step with this equation is to set it equal to 0, and I'm going to do that by subtracting sine theta. So sine theta tangent theta minus sine theta equals 0. And I'm going to factor sine theta from each term. I'll have that times tangent theta minus 1. At this point, I want to set each factor equal to 0. I set sine theta equal to 0 and tangent theta minus 1 equal to 0. Where I have tangent theta minus 1 equals 0, I'm going to add 1 to each side to get tangent theta equals 1. Now I'm looking for theta. When sine of theta, or the angles theta for which the sine is 0, are the angles 0 degrees and 180 degrees. The angles where the tangent is equal to 1, one of them is 45 degrees in quadrant 1. The tangent's also positive in quadrant 3. I use 45 degrees as a reference angle into quadrant 3, and so what I do is I add 180 degrees to 45 degrees to end up with 225 degrees as a second angle whose tangent is positive 1. For this equation, the solution set is 0 degrees, 45 degrees, 180 degrees, 225 degrees. Let's solve a trig equation. We want to solve tangent squared plus tangent minus 2 equals 0 over the interval 0 to 2 pi. Since the equation is already set equal to 0, I'm going to start by factoring, and it factors into tan x. I have tangent x minus 1 plus 2. At this point, I'm going to take each factor and set it equal to 0. And then for each factor, isolate tangent x. So here at the left, I end up with tangent x equals positive 1. At the right, tangent x equals negative 2. I'm looking for all the solutions to your working with the piece on the left, for which tangent of x equals positive 1 between 0 and 2 pi. Tangent's positive in quadrant 1 and has value 1 if x is the angle 45 degrees. Tangent's also positive in quadrant 3. I can use 45 degrees as a reference angle into quadrant 3. And actually, I need to answer this in radians, pi over 4. I'm supposed to give my answers between 0 and 2 pi. I use pi over 4 as a reference angle into quadrant 3. And so to find x in quadrant 3, I'll take pi over 4 and add pi, and end up with 5 pi over 4. Now for the second piece, to find x, there isn't an exact value of x that I know of where the tangent of that is negative 2. So to solve for x, I need to find the inverse tangent of negative 2. I've run out of room, and I've worked that part on a separate sheet of paper. To solve for x, I took the inverse tangent of negative 2, and with the help of a calculator, not in my head, I end up with negative 1.1071 and some more decimal places. Now the reason that this is negative is because of the range of the inverse tangent function. The inverse tangent function's range is from negative pi over 2 to pi over 2. This is the result I come up with, but that's not in the interval 0 to 2 pi. To find values that are in the interval 0 to 2 pi, I'm going to take negative 1.1071 and add pi. And with the help of a calculator, if you add pi, you end up with 2.0344, which is between 0 and 2 pi. Recall that 2 pi is about 6.28. I'm also going to add 2 pi to get a second solution. Again, with the help of a calculator, if you add 2 pi to negative 1.1071, you end up with 5.1760, which is less than 6.28. I could continue this pattern, but if I add 3 pi to this value, I'll get a number larger than 6.28, so I know to stop at this point. And I'm ready to write the solution set to the equation that I started with. Recall that we had pi over 4 and 5 pi over 4 as solutions, as well as 2.0344 and 5.1760. Let's solve a trig equation. We want to find all the solutions of cotangent x times cotangent x plus 3 equals 1, and we're going to write the solution set. A first step here is to distribute to get rid of the parentheses, at which point we have cotangent squared x plus 3 cotangent x equals 1. Now I want to set it equal to 0, so I'm going to subtract 1. Cotangent squared x plus 3 cotangent x minus 1 equals 0. It would be great at this point if the equation factored as if it was a quadratic. It doesn't factor, so we're going to go to the quadratic formula. Rather than writing x equals in our quadratic formula, we're going to write cotangent x equals negative b plus or minus the square root of b squared minus 4 times a, which is the coefficient of cotangent squared, times c, which is negative 1, all divided by 2 times a. And I want to simplify. I'll do a little bit here. Negative 3 plus or minus the square root of 3 squared, which is 9, and this will be plus 4 over 2. And I want to continue with that. Negative 3 plus or minus, this is going to be square root 13 over 2. So cotangent x is negative 3 plus or minus square root 13 over 2. Since I'm looking for x, at this point I would break it into 2 pieces and get decimals. What I mean is, with my calculator, find cotangent x equals negative 3 plus the square root of 13 over 2, and negative 3 minus the square root of 13 over 2. So picking up a calculator and getting a value, this particular value is going to come out to about 0.3028 with some more decimal places. Again, with the help of a calculator, getting a value, this value is going to come out to about negative 3.3028. And I need to think about finding x at this point. And I will use a calculator, but there's no cotangent button on your calculator. But remember that the cotangent and the tangent are reciprocals. So if cotangent x is this value, the tangent of x is going to be 1 over the reciprocal of that, 3028. And in a similar way, the tangent of x is going to be 1 over negative 3.3028. At this point, I'm ready to grab my calculator, so I'm going to do that. With the help of a calculator, I'm going to first do 1 divided by 0.3028 and get a value, and then I want the inverse tangent of that answer. The inverse tangent, or the angle whose tangent is that answer, comes out in radians to 1.27677 and so forth. We'll keep that answer in mind, and let's find 1 divided by negative 3.3028 as a decimal and find the inverse tangent of that answer, and we end up with negative 0.2939. Now, for this particular equation, we need to write the whole solution set, which means all infinite solutions. We're going to need to use both of those decimals. The 1.2768 will round to the fourth decimal place, and the negative 0.29. And so our solution set for this particular equation is going to be negative 0.29, and if you round, maybe 40, plus n pi, where n is an integer, as well as our other solution, which was 1.2768 plus n pi, where n is an integer. And let me attach that as a qualifier restriction. And one other comment. The reason we're adding n pi is because the period of both the cotangent and tangent, although we ended up using the tangent, the period of the tangent is pi. Let's solve a trig equation. We want to solve tan x plus the square root of 3 equals secant x over the interval 0 to 2 pi. Now, for this particular equation, as a first step, I'm going to square each side of the equation. If I square the left-hand side, multiplying things out, I'll end up with tan squared of x plus 2 times the square root of 3 times tan x plus the square root of 3 squared, which is 3. And on the right-hand side, I have secant squared of x. Now, everything on the left is in terms of tangent, so what I'm going to do is use the Pythagorean identity for secant squared and replace it with tangent squared plus 1, at which point I have tan squared of x plus 2 square roots of 3 tan x plus 3 equals tan squared x plus 1. At this point, I see that I could subtract tangent squared from each side of the equation, and I would be left with 2 square roots of 3 tan x plus 3 equals 1. At that point, I'm going to subtract 3 from each side. I'll have then 2 square roots of 3 tan x equals negative 2. I'm going to isolate tan x by dividing each side by 2 square roots of 3. Simplifying the 2's, I'll have tan x equals negative 1 over the square root of 3. And I've written that on another sheet, which, if you rationalize the denominator, is the square root of, negative the square root of 3 over 3. Now, there are two solutions to this particular statement. The tangent's negative in quadrant 2, and in quadrant 2, the tangent has value negative 1 over square root 3 if x is the angle 5 pi over 6 in radians, and that's an answer in quadrant 2. The tangent's also negative in quadrant 4, with pi over 6 as a reference angle as well in quadrant 4. X could be 11 pi over 6 as a solution, and both of these satisfy tan x equals negative 1 over square root 3. But because I squared both sides of the original equation, it's possible that one of these might be an extraneous solution. So I should check each one in the original equation. Let's start by checking x equal 5 pi over 6. And what that means is to put it into each side of the original equation. So if you look back at the original equation, putting 5 pi over 6 for x means finding the tangent of 5 pi over 6 plus the square root of 3. And that's the left-hand side. Now, if you simplify that with a calculator, or without a calculator, if you simplify it exactly, let's see, it would be negative square root 3 over 3 plus the square root of 3, which comes out to 2 square roots of 3 over 3. So that's the value that we get on the left side of the equation if x is 5 pi over 6. The right side of the equation was secant of x, but for x we're going to put 5 pi over 6. Now the secant of 5 pi over 6 comes out to negative 2 square roots of 3 over 3. These two are not the same, which means that 5 pi over 6 is not a solution to the original equation. So let's see if 11 pi over 6 is. So what we want to do at this point is we want to check x equals 11 pi over 6 in the original equation. We'll start with the left-hand side. We'll find the tangent of 11 pi over 6 and we'll add the square root of 3. The tangent of 11 pi over 6 is negative square root 3 over 3. Add that to the square root of 3 and you end up with 2 square roots of 3 over 3. That's the left-hand side when x is 11 pi over 6. Now for secant of x, or secant of 11 pi over 6, which is the right-hand side of our equation, the secant of 11 pi over 6 is exactly 2 square roots of 3 over 3. These two are the same, which means 11 pi over 6 is a solution to the equation. It's the only solution, and we write it in a solution set, 11 pi over 6. Let's work an application problem. A basic component of music is a pure tone. The graph models the sinusoidal pressure Y equal P in pounds per square foot from a pure tone at time x equal t in seconds. And what you see graphed is Y equals 0.004 sine 300 pi x. Notice on the graph that there are 6 cycles in the 0.04 seconds that you see. Continuing, the frequency of a pure tone is often measured in hertz. 1 hertz is equal to 1 cycle per second and is abbreviated Hz. What is the frequency f in hertz of the pure tone shown in the graph? Well, to get the frequency, we take the number of cycles, 6, divided by the number of seconds, 0.04. And if you divide that either by hand or with the help of a calculator, it's going to come out to 150. The units here are cycles per second, 150 cycles per second. But as we see in this description, we can call that 150 hertz, and that's the frequency. Let's continue. The time for the tone to produce 1 complete cycle is called the period. Approximate the period t in seconds of the pure tone. Well, the period t can also be found by finding the reciprocal of the frequency. In the problem that we just worked, we found the frequency to be 150 hertz. And 1 divided by 150 would be the period, the time in seconds for 1 cycle. Or you could use a decimal for that. It's 0.006, where the 6 repeats. Seconds is the period. Okay, let's continue. An equation for the graph is y equal 0.004 sine 300 pi x. We want to use a calculator to estimate all solutions to the equation that make y equal to 0.004 over the interval 0 to 0.02. So at this point, we want to go ahead and grab our calculator, turn it on, and go into y equals. In y equals, we want to enter 0.004 sine of 300 pi times x as one function. A second function is 0.004, and we're going to find the points of intersection of these two functions. Let's take a look at a window. I've set a window ahead of time. I've set my x min from 0 to 0 and my x max to 0.02 as directed. My x scale I set at 0.01. My y min I've set to negative 0.007 and my y max to 0.007 with the y scale at 0.001. And I'm going to take a look at that graph. Here's the graph of the sine function. A second graph should draw, and that's the graph of y equals 0.004, that horizontal line. Now I'm interested in finding the points of intersection, and I see that there are 3 of them. Using the calculator, I'm going to go to Second Calc, Option 5, which is called intersection. Now I want to enter on the two curves, but I also want to get close to a point of intersection. So I'm going to get a little bit closer to this particular point of intersection. I'll enter and call this my first curve. Notice that the cursor jumps to the horizontal line, and I'll enter and call that my second curve. I'll move my cursor just a little closer to the point of intersection before I push enter. And the calculator runs its intersect program, and it tells me that particular point of intersection is x equals 0.00833333, and so forth. If I were to run that program 2 more times, once for each of the other points of intersection, the first point of intersection would come out to 0.0017, and the third 0.015. Let's take a minute to write those on our paper. The 3 solutions are x equal 0.0017, x equal 0.0083, and x equal 0.015.